Introduction to DS-Lite. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving into DS-Lite, which stands for Dual Stack Lite. This is a fascinating IPv6 transition mechanism that was standardized in RFC 6333 back in 2011. DS-Lite represents one of the most elegant solutions to a fundamental problem that ISPs face. That problem is, how do you continue providing IPv4 services to customers while transitioning your network infrastructure to IPv6? The beauty of DS-Lite lies in its approach. It essentially tunnels IPv4 traffic through an IPv6-only infrastructure, allowing ISPs to eliminate IPv4 from their core network while still supporting IPv4 applications for their customers. The architecture of DS-Lite consists of two main components. On the customer side, we have what is called the Basic Bridging Broadband Element, or B4 for short. This device sits at the customer premises and handles the encapsulation of IPv4 packets into IPv6. On the ISP side, we have the Address Family Transition Router, abbreviated as AFTR. The AFTR performs the critical function of decapsulating the tunneled traffic and providing NAT for the private IPv4 addresses used by customers. This two-component architecture creates a clean separation between the customer's IPv4 requirements and the ISP's IPv6-only infrastructure. What makes DS-Lite particularly compelling for ISPs is the operational efficiency it provides. By running IPv6 only in the core network, ISPs can dramatically reduce the complexity of their routing tables. This eliminates the need for maintaining dual-stack infrastructure throughout their network. And, most importantly, it allows them to conserve precious IPv4 address space by using large-scale network address translation at the AFTR instead of assigning public IPv4 addresses to every customer. ISPs can use private IPv4 addresses at customer sites and perform centralized NAT at the AFTR. This allows a single public IPv4 address to serve hundreds or even thousands of customers. B4 Element Architecture. Let's examine the B4 element in detail, as it's the foundation of the DS-Lite solution from the customer perspective. The B4 element is typically implemented in the customer's home router or CPE device. Its primary responsibility is to create an IPv4 in IPv6 tunnel that carries the customer's IPv4 traffic across the ISP's IPv6-only network. The B4 maintains what appears to be a standard IPv4 network on the customer side. Devices on the home network receive private IPv4 addresses through DHCP. They communicate using IPv4 protocols, and they are completely unaware that their traffic will be tunneled through IPv6. The B4 element needs to be configured with several critical pieces of information. First and foremost, it requires an IPv6 address for itself. This is typically obtained through DHCPv6 or SLAAC from the ISP. The B4 also needs to know the IPv6 address of the AFTR, which is the tunnel endpoint on the ISP side. This AFTR address can be configured statically, obtained through DHCPv6 options, or discovered through DNS. The B4 assigns private IPv4 addresses to devices on the customer network, typically from the RFC 1918 address space. These are the same private addresses that have been used for decades in home networks. When an IPv4 packet arrives from a device on the customer network, destined for the Internet, the B4 performs IP and IP encapsulation. It takes the entire IPv4 packet, including the IPv4 header with source and destination addresses, and wraps it inside an IPv6 packet. The source IPv6 address is the B4's own IPv6 address, and the destination IPv6 address is the AFTR's IPv6 address. The protocol field in the IPv6 header is set to 4, indicating that the payload is an IPv4 packet. This creates a tunnel that carries IPv4 traffic transparently across the IPv6 network. The beauty of this approach is that the IPv6 network treats these packets as standard IPv6 traffic. It does not need to understand or process the IPv4 payload at all. AFTR element architecture. The AFTR element is where the magic really happens in the DS-Lite architecture. This component sits at the ISP's network edge and serves as the bridge between the ISP's IPv6-only infrastructure and the dual-stack Internet. The AFTR receives tunneled IPv4 in IPv6 packets from potentially thousands of B4 elements, decapsulates them, performs NAT, and forwards the resulting IPv4 packets to their destinations on the IPv4 Internet. It also handles the reverse process for return traffic, encapsulating IPv4 packets back into IPv6 and sending them to the appropriate B4 element. The AFTR maintains a sophisticated NAT state table that tracks active connections for all the B4 elements it serves. This table maps the combination of private IPv4 address and port number from the customer side to a public IPv4 address and port number on the Internet-facing side. Unlike traditional NAT devices that serve a single location, the AFTR performs what is called carrier-grade NAT or CGN. It simultaneously manages NAT sessions for thousands of customers, each potentially having dozens or hundreds of active connections. The AFTR must allocate port numbers efficiently across its pool of public IPv4 addresses to ensure it can support the massive number of simultaneous connections required in a carrier environment. Performance and scalability are critical concerns for AFTR implementation. The device must be capable of processing high packet rates while maintaining accurate NAT state for millions of concurrent sessions. It needs sufficient memory to store the NAT translation tables, adequate processing power to perform encapsulation and decapsulation at wire speed, and robust session management to handle connection timeouts and state cleanup. Many ISPs implement AFTR functionality using high-performance hardware or distribute the load across multiple AFTR devices using anycast addressing. The AFTR also needs to support logging and troubleshooting capabilities, as the additional layer of NAT can complicate network diagnostics and may be subject to regulatory requirements for connection logging in some jurisdictions. Packet flow and encapsulation. Understanding the complete packet flow in DS-Lite is essential to appreciating how the technology works end-to-end. Let's walk through a typical scenario where a customer device wants to reach a server on the IPv4 Internet. The customer device, let's say a laptop with IP address 192.168.1.100, initiates a connection to a web server at a public IPv4 address. The laptop creates a standard IPv4 packet with its private source address and the server's public destination address, along with source and destination port numbers for the TCP connection. This IPv4 packet reaches the B4 element, which could be the customer's home router. The B4 examines the packet and recognizes that it's destined for the Internet, not for another device on the local network. The B4 then performs IPv4 in IPv6 encapsulation. It constructs a new IPv6 packet where the payload is the entire original IPv4 packet. The IPv6 header contains the B4's IPv6 address as the source, something like 2001:db8:1:100, and the AFTR's IPv6 address as the destination, perhaps 2001:db8:FFFF:1. The next header field in the IPv6 header is set to 4, indicating that an IPv4 packet follows. This encapsulated packet then travels across the ISP's IPv6-only network, being routed based purely on the IPv6 addresses in the outer header. When the packet arrives at the AFTR, the device decapsulates it by removing the IPv6 header and extracting the original IPv4 packet. The AFTR then examines this IPv4 packet and performs NAT. It replaces the private source IP address 192.168.1.100 with one of its public IPv4 addresses, for example 203.0.113.50, and allocates a source port number from its available pool. The AFTR records this mapping in its NAT state table, associating the customer's private address and port with the public address and port, along with information about which B4 element originated the connection. The translated IPv4 packet is then forwarded to the destination server on the IPv4 Internet. Return traffic follows the reverse path. The AFTR receives IPv4 packets destined for its public addresses, looks up the appropriate B4 and private address in its NAT table, encapsulates the packet in IPv6, and sends it through the tunnel to the correct B4 element. IPv4 address space conservation. One of the primary motivations for deploying DS-Lite is the dramatic improvement in IPv4 address utilization it provides. In traditional broadband deployments, each customer receives at least one public IPv4 address, which means an ISP serving 1 million customers would need 1 million IPv4 addresses just for residential broadband. With global IPv4 address exhaustion, this model became unsustainable years ago. DS-Lite fundamentally changes this equation by allowing ISPs to serve thousands of customers with a single public IPv4 address through the carrier-grade NAT functionality of the AFTR. The address sharing ratio, the number of customers sharing each public IPv4 address, depends on several factors. Each AFTR has a finite pool of public IPv4 addresses and a finite number of ports per address. With standard TCP and UDP, each address has 65,536 possible port numbers, but some of these are reserved or commonly used for specific services. A conservative approach might allocate 200 to 500 ports per customer, which would allow 100 to 300 customers to share a single public IPv4 address. More aggressive deployments might push this to 1,000 or more customers per address, though this increases the risk of port exhaustion and can cause problems for applications that require many simultaneous connections or specific port ranges. The impact on ISP operations is profound. An ISP that previously required a /10 IPv4 allocation, which translates to over beginning with 40 ending with 00 addresses, to serve its customer base, might now operate with just a /18 or /19 allocation. This allocation provides somewhere between 8,000 and 16,000 addresses for the same number of customers. This represents a reduction in IPv4 address requirements by a factor of 250 or more. The savings extend beyond just address acquisition costs. With fewer public IPv4 addresses in use, routing tables are smaller, BGP convergence is faster, and the overall complexity of managing IPv4 infrastructure is reduced. These operational benefits compound over time as the ISP continues to grow its customer base without requiring proportional growth in IPv4 address consumption. Configuration and deployment. Deploying DS-Lite requires careful planning and configuration of both B4 and AFTR elements. On the customer premises equipment side, the B4 configuration can be relatively straightforward if the CPE supports DS-Lite natively. Modern home routers from major vendors often include DS-Lite support that can be enabled through the web interface or configuration file. The B4 needs to be configured with the AFTR's IP version 6 address, which ISPs typically provision through DHCP option 64 as defined in RFC 6334. This allows for centralized management and easy updates if the AFTR address needs to change. On Linux-based systems, DS-Lite functionality can be implemented using the IP command and network namespaces. Creating a DS-Lite tunnel involves several steps. First, you configure an IPv6 address on your external interface using either DHCPv6 or SLAAC. Then you create an IP6TNL tunnel interface, specifying the mode as IP-IP6, which indicates IPv4 in IPv6 encapsulation. The local IPv6 address is your B4's address, and the remote address is the AFTR's IPv6 address. You then configure an IPv4 address on this tunnel interface, typically from the RFC 1918 private space, and set up routing to send all IPv4 traffic through the tunnel. NAT configuration using IP tables allows the B4 to serve multiple devices on the customer LAN. The AFTR configuration is considerably more complex due to the scale and performance requirements. The AFTR device needs to be configured with one or more public IPv4 addresses for NAT, IPv6 connectivity to receive tunnel traffic from B4 elements, and sophisticated NAT policies to manage port allocation across thousands of customers. Many ISPs use dedicated carrier-grade NAT devices or high-performance software implementations running on powerful server hardware. The AFTR must also implement connection tracking to maintain state for millions of concurrent NAT sessions, properly handle session timeouts, and potentially log connection information for regulatory compliance. Configuration typically includes setting port allocation policies, defining port ranges per subscriber, implementing fair usage policies to prevent individual customers from monopolizing ports, and configuring monitoring and alerting for capacity management. Advantages and challenges. DS-Lite offers several compelling advantages that have made it popular among internet service providers globally. The most significant benefit is the complete elimination of IPv4 from the ISP's core network infrastructure. This simplification reduces operational complexity, lowers equipment costs, and allows the ISP to focus on building a modern, scalable IPv6 network. By consolidating IPv4 handling at the AFTR edge devices, ISPs can avoid the complexity and expense of maintaining dual-stack routing throughout their entire network. The IPv6-Only core also provides better scalability, as IPv6 a vast address space eliminates many of the constraints that made IPv4 networks difficult to manage at scale. The dramatic reduction in IPv4 address consumption is another major advantage. Through carrier-grade NAT at the AFTR, ISPs can reduce their IPv4 address requirements by factors of 100 or more compared to traditional deployments. This not only conserves a scarce global resource but also provides significant cost savings for ISPs that would otherwise need to purchase expensive IPv4 address blocks on the transfer market. DS-Lite also provides a clear migration path toward an IPv6-only future. Customers can continue using their IPv4 applications without disruption while the ISP builds out its IPv6 infrastructure. As more services become available over IPv6, the load on the AFTR decreases naturally over time. However, DS-Lite does introduce several challenges that must be carefully considered. The additional layer of NAT can cause problems for certain applications and protocols. Peer-to-peer applications, online gaming, and services that require inbound connections face difficulties because the customer's device sits behind carrier-grade NAT. Port forwarding becomes much more complex or impossible, as the customer doesn't control the public-facing NAT device. The AFTR represents a potential single point of failure and bottleneck. All IPv4 traffic must pass through this device, so it requires redundancy, high availability, and substantial capacity. The additional processing for encapsulation, decapsulation, and NAT introduces latency compared to native IPv4 or IPv6 connections. For latency-sensitive applications like real-time voice or gaming, this overhead can impact user experience. Troubleshooting becomes more complex with the additional tunneling layer, and regulatory requirements in some jurisdictions may require logging connection information, which adds storage and processing overhead at the AFTR. DS-Lite versus alternative solutions. To fully appreciate DS-Lite's role in the IPv6 transition landscape, it is valuable to compare it with other transition mechanisms. Traditional dual-stack deployment. where every device and router runs both IPv4 and IPv6 simultaneously, remains the gold standard for compatibility. However, it requires substantial IPv4 address resources and operational complexity. The ISP must maintain two complete routing infrastructures in parallel. This doubles the management burden and equipment requirements. Dual stack works well for organizations with adequate IPv4 addresses, but it becomes impractical for large ISPs facing address exhaustion. NAT64 with DNS64 takes a different approach by translating between IPv6 only clients and IPv4 only servers at the network edge. This solution allows the ISP to deploy IPv6 only to customer premises, eliminating IPv4 entirely from customer devices. While this provides excellent IPv4 address conservation, it requires that customer devices support IPv6, which wasn't always feasible when NAT64 was first deployed. DS-Lite has an advantage here because it allows customers to continue using IPv4 applications on IPv4 addressed devices without requiring any client-side changes or IPv6 support on end-user devices. 464XLAT combines elements of both approaches. It runs NAT64 in the core network, but adds a customer-side translator, called CLAT, that converts between IPv4 applications and the IPv6-only network. This provides the best of both worlds: IPv4 application compatibility and an IPv6-only network infrastructure. However, 464XLAT requires support on customer devices, typically at the operating system level, which has limited its adoption primarily to mobile networks where carriers control the device software. DS-Lite, by contrast, only requires support in the CPE device, which the ISP can control and provision. Lightweight 4/6 is another alternative that distributes NAT functionality to the customer premises rather than centralizing it at the AFTR. This reduces the processing load at the ISP edge but requires more sophisticated CPE and more complex provisioning. For most ISPs, DS-Lite's balance of simplicity, compatibility, and address conservation makes it an attractive choice, particularly during the transition period while IPv4 services remain essential. Real-world implementation. Let's walk through a practical implementation scenario to see how DS-Lite works in a real deployment. Consider an ISP that has transitioned its core network to IPv6 only and deployed AFTR devices at 2 key locations for redundancy. The AFTR devices are configured with a pool of public IPv4 addresses and are advertised via anycast, so B4 elements automatically connect to the nearest AFTR based on routing. Each AFTR is configured to handle hundreds of thousands of concurrent NAT sessions and is provisioned with enough IPv4 addresses to serve the expected customer base with a sharing ratio of about 200 customers per address. When a new customer subscribes to the service, the ISP provisions a CPE device that includes B4 functionality. This could be a commercial router with DS-Lite support or custom firmware. During the initial connection, the CPE obtains an IPv6 prefix via DHCPv6 prefix delegation. It also receives DHCP option 64, which contains the anycast IPv6 address of the AFTR devices. The CPE configures itself as a B4 element, creating the IPv6 tunnel to the AFTR and setting up a private IPv4 network for the customer's devices. From the customer's perspective, they receive IPv4 addresses via DHCP, just like they would with any other internet service. The underlying DS-Lite mechanism is completely transparent. As customers use the service, their IPv4 traffic flows through the tunnels to the AFTR. The ISP monitors AFTR performance metrics including tunnel count, NAT session count, port utilization per public IPv4 address, and packet processing rates. If an AFTR approaches capacity, the ISP can deploy additional AFTR devices and adjust anycast routing or provisioning to distribute load. The system scales horizontally by adding more AFTR capacity as the customer base grows. Over time, as more Internet services become available over IPv6, the ISP observes increasing amounts of native IPv6 traffic that bypasses the DS-Lite infrastructure entirely. This natural evolution reduces the load on AFTR devices and provides a graceful migration path. Some ISPs implement policies to encourage IPv6 adoption, such as providing higher bandwidth or lower latency for native IPv6 connections compared to tunneled IPv4 traffic. Future of DS-Lite. As we look toward the future, DS-Lite's role continues to evolve alongside the broader IPv6 transition. We're now well over a decade past IPv4 address exhaustion, and the percentage of Internet traffic carried over IPv6 continues to grow year over year. Major content providers like Google, Facebook, and Netflix serve the majority of their traffic over IPv6 in regions with good IPv6 deployment. This trend reduces the burden on DS-Lite infrastructure because traffic that uses native IPv6 doesn't need to traverse the AFTR or consume IPv4 addresses. For ISPs running DS-Lite, this means the AFTR becomes progressively less critical to network performance over time. However, IPv4 services are likely to remain relevant for many more years. There are millions of IPv4-only servers and services on the Internet, legacy devices that will never be updated to support IPv6, and organizations that have no immediate plans to deploy IPv6. DS-Lite provides ISPs with a sustainable way to continue supporting these IPv4 requirements without the operational burden of maintaining dual-stack infrastructure throughout their networks. The technology has proven robust and scalable in production deployments worldwide, with many ISPs successfully serving millions of customers through DS-Lite infrastructure. Looking ahead, we may see hybrid approaches become more common. ISPs might deploy DS-Lite for residential customers while using 464XLAT for mobile networks, or implement LW406 for business customers who need more control over their IPv4 connectivity. The key insight is that DS-Lite represents one tool in a toolkit of transition mechanisms, each with its own strengths and appropriate use cases. As IPv6 deployment continues to mature, the importance of these transition technologies will gradually diminish, but DS-Lite has secured its place in Internet history as an elegant and practical solution to one of the most challenging technical problems of the IPv6 transition era. For network engineers and architects working on IPv6 deployments today, understanding DS-Lite provides valuable insights into the trade-offs between compatibility, scalability, and operational complexity that define modern network design. Thank you for your attendance. Please consider subscribing to the channel.